Hey everyone, how's it going? This is the second episode of PBR texture maps in Blender. This time we'll take a look at what normal maps are and how they work. Let's begin. A normal map provides detailed surface texture by altering how light interacts with the surface, creating the illusion of depth and surface details without modifying the actual geometry. Let's break down what a normal map is and how it works. A normal refers to the direction a face is pointing. In Blender, you can display normals by entering Mesh Edit mode, going to Overlays, and enabling the option to display normals. A flat shaded surface has normals pointing in the same direction as the faces. When we right-click and select Shade Smooth, the surface normals are interpolated, creating the illusion of a smooth surface. In this example, we have a version of the same object with some displaced geometry in the center. We can capture the normal data from these deformed faces and store it in what's called a normal map. The diagram shows how the direction each face is pointing is encoded into a 2D normal map. By applying this normal map to our original smooth shaded object, we can trick the lighting into reacting as if the surface is deformed, even though it remains flat. Additionally, this diagram illustrates the surface normals with both smooth shading and the normal map information applied. Let me show you how Blender uses colors to represent surface direction, which will help you understand the relation between Blender and normal maps. Here is the default Blender cube, with faces pointing in each direction. The directions the faces are pointing are represented by normals. The normals point along each axis of the x, y, and z coordinates. Now, if I connect the normal output of a texture coordinate node into the material output surface socket, we can see that each direction the faces are pointing are represented by an RGB color. This is because each axis coordinate x, y, and z corresponds to an RGB value. When x is 1, the color becomes red. When y is 1, the color becomes green. And when z is 1, the color becomes blue. When all of the x, y, and z coordinates become 0 or negative, the faces are clamped to black, because RGB only ranges from 0 to 1 and does not support negative values. Next, let's take the example of a sphere. Here we can also see the normals describing the orientation of each face. However, unlike the cube, the normals are not pointing directly in one direction. But each one of these normals are still mapped to x, y, and z coordinates between -1 and 1. And each of these coordinates are still mapped to an RGB value. However, since the normals don't point directly in one direction, they result in different combinations of red, green, and blue. Red and blue becomes purple. Green and blue becomes teal. Red and green becomes yellow. Also, when we right-click and select Shade Smooth, these values create a smooth color gradient, just like with any shader. And just like with a cube, whenever a coordinate becomes negative, that value is clamped to 0. In this example, both the y and z axes are negative, so the green and blue values become 0, leaving only the red from the positive x-axis. Here, the z value is negative, but the x and y values are positive. As a result, the blue is 0, and the blend between red and green creates this yellow color. In this case, the x and z axes are negative, so the red and blue are 0, while the positive y-axis leaves only green. Now, with the z-axis positive and the x and y negative, only the blue remains. The closer each axis gets to negative, the lower the corresponding RGB value becomes, making the color appear darker. Finally, when all axes are between 0 and -1 at the same time, all RGB values are clamped to black. To summarize, these demonstrations with a cube and sphere illustrate how surface normals in Blender's 3D space correspond to RGB colors. Now let's talk about how this relates to normal maps. Here we have a sphere's normals baked onto a normal map. This baked normal map mimics the appearance of the sphere's surface and curvature without the actual geometry. We want to store all the orientation information from -1 to 1 on each axis. But the image can only store RGB values between 0 and 1. Therefore, the normal values of our sphere need to be compressed into RGB values. And it works like this. All the values from -1 to 0 XYZ get compressed into RGB values from 0 to 0.5. Then all the values from 0 to 1 XYZ get compressed into RGB values 0.5 to 1. In this way, our normal map is able to store angle information from both the negative and the positive directions using only RGB values. In Blender, when the z-axis value is 0 and the blue channel of an RGB normal map is set to 0.5, the normal is oriented such that it is neither pointing upward nor downward. Instead, it is directed straight to the side. However, when blue values fall short of 0.5, the normals start to point downward. This orientation is uncommon in normal maps, which typically aim to enhance surface details, while keeping normals facing outward or sideways. In fact, when normals are facing the wrong direction in Blender, you're most likely going to experience shading issues. To check if you have normals pointing in the wrong direction, you can enter Overlays and turn on Face Orientation. This will display faces pointing correctly outward in blue and faces pointing incorrectly inward in red. To fix this problem, you can select your faces in Edit mode and press Shift-N to recalculate normals. And this should make the shading artifacts from incorrect normals go away. Let me demonstrate how blue values rarely go below 0.5 using a concave version of the normal map for the sphere. First, consider the convex version of the normal map for the sphere, where the x and y values point outward in their respective positive and negative directions. With the light source coming from the right, the normals seem to create a convex spherical surface. When the normal map is concave, these directions are flipped. The negative directions start pointing positive, and the positive directions start pointing negative, creating the illusion of depth. Despite this, as you can see, the blue value remains oriented outward, typically close to 1, except for in areas where the normals start pointing to the side. In fact, the soft purple or cyan color most commonly seen on normal maps indicates flat areas where the surface is pointing directly outward. And as we know, when a face points directly outward, the red and green values are 0.5 and the blue value is 1, which creates this color. Now that we understand normals in Blender, we know that they are vectors with coordinates ranging between -1 and 1 on the x, y, and z axes. These values determine the direction in which faces point in 3D space. When we bake the normals of a sphere onto a plane, we create a normal map. However, a normal map can only contain RGB values between 0 and 1, so the Blender vectors are compressed into this range. To use these normal maps in Blender again, we need to connect the normal map to the color socket of a normal map node. This node converts the values back into vector coordinates. As you can see, the colors of the normal map are consistent with those of the original sphere. Finally, we plug the normal map node into the normal socket of the principled shader to use it in our renders. We need to set the normal map to non-color space because we're extracting the normal data from the map, not displaying its RGB colors. The normal map node should be set to tangent space, because the normal map we are using is a tangent space normal map. In the next video, I'll go over some more practical details, like the differences between tangent space, object space, and world space, the difference between OpenGL and DirectX, and a comparison between normal maps and bump maps. Thanks for watching, I'll see you in the next one.